We'll get started here in a second. Okay, let me share my screen with you so I can tell you what we're doing today. So this week we're going to be practicing some more impulse momentum ideas, conservation momentum stuff, because I would like to have a test a week from today, or test quiz. It's not going to be a full 100-point test or anything, but it's going to be kind of like the last thing we're able to do. And so today we're going to be whiteboarding the very last problem on worksheet 1, and I'll share that with you in a second, or I've already shared it with you, but I want to talk about it. Then we'll get started on worksheet 2, and then for homework, I would like you to get started on worksheet 3, and I'll show you where that's at, and there's a little quiz over what we're doing today. Okay, so worksheet 1 I shared with you some time ago, but we didn't have time to do number 9. So number 9, part A, we have a golf ball that's being dropped from a certain amount of height. And for part A, what I'd like you to do is draw the motion map. And the motion map, it says it's a totally perfectly, I shouldn't say perfect, it's an elastic collision. And so I would like you to draw the motion map from when it's above the floor to where it hits the floor, and then it bounces back up to the same height. So it's kind of important you draw the motion map there. So spend your time on it, because I want to talk about that. And then part B should be kind of easy. It's just kinematics, finding the time it takes. All right, so let me stop sharing and open up the breakout room so you guys can go there then. Carter, you should have got an invitation. If you didn't, it is room 5 at the bottom. You can join room 5. Okay, instead of sharing a screen, having somebody share a screen, I'm just going to share my screen with you, and you kind of look at it. Let me know if you have questions about it. Okay. Okay, so for the motion map for this, I have the ball falling here on the left-hand side, and notice the spacing is getting further and further. This bottom part is like a big Uber dot because it's almost instantaneous where it goes down and comes back up. It's not truly instantaneous, but it's pretty close. It happens very quickly. And then on the way up, it still has the same acceleration of gravity downward, and so it slows down at that same rate. Okay, so, and it goes back up the same height because we're saying it's an elastic collision, which means energy is conserved. Kinetic energy is conserved, I should say. Kinetic energy is conserved, which means it goes up to the same height. The thing I really wanted to point out, that's why I wanted you to take some time to draw this, is because right at the bottom, there is an acceleration that is actually upward. Okay, and that is causing this impulse. So there's some force on it at the bottom that causes the impulse. So what force is that exactly at the bottom that causes the impulse? If you could unmute yourself. What force causes the impulse when it hits the floor?
Whatever normal force.
Yeah, it's a normal force, right? And so the reason why I want to point that out is usually in our heads we often think the normal force is the same as the gravitational force, but it's not always. And in fact, in this case here, this normal force right when it hits is going to be pretty big at its maximum. And so I think it's kind of interesting to consider that. Determining a time, you just have to do kinematics. Can you guys again unmute yourself and tell me what time you guys got?
0.447 seconds.
Yeah, that's what I got too. I use D equals VIT plus 1/2 AT squared, and I got about 0.45 seconds. Okay, any questions on that? Give me a thumbs up if you get that, no problem. Yeah, okay. All right, so the next one we're gonna be doing, so that's problem number 9, part A and B. Now we're gonna do part C and D. And what you're doing for C is you're finding what the instantaneous momentum is. So you're going to have to do a little bit of kinematics to figure out the speed right before it hits, and then figure out the momentum. And then part D, you're finding the change in momentum. So that's the impulse. So remember, it's an elastic collision. So that should help you figure out what the velocity is right when it leaves the floor. So you should be able to figure out the momentum and then figure out the change in momentum. All right, so let me stop sharing and let you go back in your groups, your breakout rooms. Listen, you should get an invitation. If you didn't, you're in room 8. So at the bottom, if you click on the breakout rooms and then go into room 8. There you go. Okay. All right, so hopefully you had enough time to look at that. Again, on this one, I think I'm just going to share my screen. If there's something that you're not sure of, or you didn't get that, you don't understand, please say something, okay? Okay, so for this one, I had to do kinematics first to figure out the speed. So I'm assuming you guys did that too. What'd you end up getting for the speed? If you can unmute yourself, what was the speed you got?
4.4 meters per second.
So everybody get that? Yeah, give me a thumbs up if that's what you got. Thumbs up, okay. There's also at the reactions at the bottom, you can do thumbs up. Okay, yeah, that's what I got. I used VF squared equals VI squared plus 2AD. You didn't have to do that. You could use the time in the previous part, but I thought that was pretty easy. And then figure out the momentum. I did mass times velocity, and I got 0.2 kilograms times meters per second. The truth is, my answers aren't exactly right. So if that's what you got, you're just like me. My answers aren't right, neither are yours exactly, because these are vectors. I really should have said downward. So the velocity is 4.47 meters per second downward. The momentum is 0.2 kilograms times meters per second downward. And it sounds like no big deal, but it is kind of important. All right, and then for the next part, the change in momentum. Well, I think I want to go back to this picture here in the previous one. We just found out what the momentum was downward. Realize that the momentum upward is going to also be that 0.2 kilograms times meters per second, but now it's upward. So a lot of times students are like, oh, they're both 0.2, 0.2 minus 0.2, 0. That's not right. They're in different directions. So I said that my initial was negative and my final is positive. So final minus a negative initial ends up making it even bigger. So I end up getting 0.2 minus a negative 0.2. I get 0.4 kilograms times meters per second. Okay, any questions? Thumbs up if you understand that. Yeah, thumbs up or the reaction thing. Okay, so no question. All right, so then the last one we're doing on this worksheet is 9E. And so it tells you that it's in contact with the floor for this amount of time, and you're supposed to figure out what that force is from the floor. So let me go ahead and open up the breakout rooms again, and you guys go ahead and work it out. Okay, so again, I'm going to share my screen with you. So for this, I drew the picture. Actually, it's the same picture I had in first part A and B. And I'm trying to figure out what this force is down here at the bottom. So first of all, I want you to understand that when it collides with the floor, it's not going to be a constant force. In other words, the force time graph would look something like this. And in fact, I think I want to show you a little video clip. So I'm hoping that you can see this. This is Time Warp. I'm not sure if you're into that from Discovery Channel. But what they're doing here is they're doing a slow motion video of a baseball hitting a baseball bat. So.
All set up? Okay. At 10,000 frames per second, we can see the regulation heart.
So what I want you to see there is it's not an instantaneous hit. There's actually kind of a squishing, and as you squish it, you can almost think of it as like a spring. As it gets more and more compressed, the force is getting bigger and bigger. And as it gets less and less compressed, the force is getting smaller. So that's going to be the same for the golf balls as well.
Right here, you can see the ball is actually.
Okay, so let me go back to this problem. So the force actually would look like this kind of this curve here, sort of, okay? Well, since it didn't give me an equation for this, and so I can't integrate it, I want you to understand that I could just find the average force. In fact, I've got a little rectangle here that's dotted line, and I want you to look at the area of that rectangle. It's about the same as the area of this curve, which means that the height of that rectangle would be kind of like the average force. And so if you took that force times the base, the time, that would give you the impulse. Okay, and that's kind of what I did for this problem. I took the average force times the time they give me, and that's going to be equal to the impulse I just found of 0.4. And so I solved it, and I got 1,006 newtons, and this time I was smart enough to include the direction. It's upward. So any questions on that? Are you guys good with that? Thumbs up if you're okay. Yeah, okay. All right, so we're done with that worksheet. Now the next thing we're doing, actually, let me go back to here. We're doing worksheet 2, which I shared that with you as well. So let's see if I can find that. So the first one we're doing, we have this train that's being assembled. Okay, so we have this train that car that's empty and it's moving at 3 meters per second and it's moving toward a loaded box car. So it kind of looks like this. So this blue one here, it's moving. It's moving toward this empty one or this other one that has the same mass, and it has a load of lumber or something inside of it. After it collides, it's going to kind of move together. So let me make this. There we go. They're going to move together. Oh, I forgot to put an arrow. Yeah, I think it's going to go a little slower. Anyway, so I need to explain what this conservation diagram is up here, right? Because at first, your students are usually kind of confused. So I kind of want to do this one together, okay? The truth is we won't spend hardly any time on these diagrams. I'd say 90% of the students really get these problems, no problem. They're like, oh, I get this. This is like easiest stuff we've done all year. But for the few people that do have a hard time with it, sometimes these diagrams help them. So let me explain what these are. So let me move these out of the way. So ignore these two here, okay? In fact, let's move this one out of the way too. Dang it. Okay. So this blue square rectangle here represents this first car. And notice that its mass is only 9,000 kilograms. It's a lot lighter inertia, has a lot less inertia than the other one, because the other one is also 9,000 kilograms, but it has 55,000 kilograms of lumber. So let's see, that's about So in other words, it's about 6 times more massive than the blue one. Okay, but that blue one's moving at 3 meters per second. So what I did was I made it 3 hash marks long to the right horizontally, but I didn't make it very wide. So in other words, it's not this wide because it's not that massive. The empty one is very, very small mass. So I'm making it about 1/6 the other one. Now for the full one, I'm just going to use red, not yellow. Red's going to represent the full one. It has much more mass. In fact, it's about 6 times more massive. So this blue one must be about 1/3 of one of those blocks. This one here would be a total of 6 of those thirds. And the truth is, it's not any width this way horizontally. It's actually 0 because it's not moving. But I couldn't really draw that. I wanted you to be able to see the red. So I don't think I can make it. Oh, there we go. Okay, afterwards, they're going to get stuck together. Okay. But I want you to understand the total area over here. If I add up the red area, which is 0, and the blue area, which is about 1/3 times 3, so about 1 whole block, that's how much total, the area is kind of like the momentum. That's how much total area I need to have over here for the final. So these two are stuck together. And remember, the red one is 2 units high, and the blue one is only 1/3 of a unit high. So it's kind of like 2 1/3. So we need 2 1/3 times something to give us 1 whole block. And so that's kind of how I figured out the width here. I don't know, maybe it's a half or whatever. So I want you to understand the total area over here on the right has to be equal to the total area over here on the left. And I can't really make this go any smaller, unfortunately. The red really is 0. Maybe I'll just get rid of it. The red's 0. So hopefully the area of the two kind of look about the same. So I don't really need you to make a conservation momentum chart. What I need you to do is I need you to write equation, conservation momentum equation, and solve for the speed. But before we do that, the one thing I haven't answered up here is what kind of event this is. And let me tell you your options. We're going to say it together. You're unmute yourself in a second. The options are, it's an explosion, it's elastic kind of collision, it's inelastic collision, or it's perfectly inelastic collision. So it's explosion, elastic collision, inelastic collision, or perfectly inelastic collision. So can you unmute yourself? What kind of event is this?
Perfectly
Perfectly
inelastic.
inelastic.
That's it, perfectly inelastic. They get stuck together, they move together with the same velocity. All right, so this is problem number 1. So let me go ahead and open up the breakout rooms for you. Solve for the speed. Okay, to save time, if you remember, I said usually students find this section like some of the easiest stuff we've done all year, and I don't want to beat you guys over the head with this. To save some time, I thought perhaps we could just simply all unmute ourselves. Could you unmute yourself? And tell me what speed you found. What speed did you find?
0.422.
0.32.
9.
Okay, so
0.3699.
okay, so it sounds like maybe
Yeah,
we got different answers then, because I'm hearing different answers. So the conservation momentum equation, you would have the mass of the blue one times the velocity of the blue one plus the mass of the red one times the velocity of the red one would be the initial momentum, and it would also be the final momentum. And so the initial momentum, I think you find to be 27,000, and set that equal to 9,000 times V, and then 64,000 times V. So maybe some of you accidentally put 55,000 times V. It's really 55,000 plus 9,000. And so I think you end up getting 0.369 or so, 0.37 meters per second. Any questions on that? Because I was hearing different answers. I think I heard 0.4 from some people. Okay. Any questions? No questions? Okay. So let me talk about the next one then. So the next one, we have an astronaut. The astronaut's holding on to this oxygen tank, and they're just sitting there. And then the astronaut's going to throw the oxygen tank, and so the oxygen tank's going to start moving in one direction. And because of that, the astronaut's going to recoil in the opposite direction. So again, I kind of want to show you the conservation momentum chart. Before this is thrown, the truth is both of these have zero momentum. I'm only showing it to you so you can see kind of the different colors. I'm going to have the blue be the astronaut and the red be the oxygen tank. Notice the mass of the astronaut is 80. The mass of the oxygen tank is 10. So in other words, the mass of the astronaut's 8 times bigger. So that's why that blue bar is about 8 times taller than the red bar. Okay. Afterwards, and they both actually would have 0 width. But afterwards, when you have the red, which is the ball kind of moving this direction, I should change, let me change the color of it red. As the ball's moving this way, it's moving at 2 meters per second. That's why I made the width of this. I try to make it 2 bars to the right. The total area of that red square has to be the same as the blue rectangle, not square, I guess, rectangle. And so let's see, if it's 8 times bigger, it's 4. So I believe the width, or I should say the height of that red rectangle is 1/4 of a unit, and it's 2 units this way. So 2 times 1/4 would tell you the total area. That's got to be the same as the total area of the blue one. So again, if you had a hard time in the last one, you didn't get the right answer, maybe these tables would help you a little bit, kind of visualize what the equation is. So what I want you to do in this problem is, again, write the conservation momentum equation and then solve for the speed of the astronaut. So let me stop sharing and open up the breakout rooms. So again, could we just simply say our answer to see if we need to go over this? So if you could please unmute yourself. And what'd you get for the speed of the astronaut?
0.25.
0.25?
Direction.
0.25? And it would be in the opposite direction. Good. So do we need to go over that one? No?
Yes.
Oh, we
please.
do. Okay. All right. Okay. Whoops. I need to share, of course. Duh. All right. So for this one, my conservation momentum equation would look like this. Pi equals Pf. Okay. Initially, the ball hasn't been thrown or anything yet, so they're just it's kind of holding there. Okay. Oh, by the way, did we talk about what kind of event is this? What kind of event is this? The options are explosion, elastic collision, inelastic collision, or perfectly inelastic collision. What kind is this one? Everybody, can you unmute yourself? What,
Explosion.
this is an explosion, right? So the initial momentum here, since it's not moving, nothing's moving, is 0. That's the initial momentum. The final momentum is going to be the mass of the astronaut times the velocity of the astronaut plus the mass of the oxygen tank times the velocity of the oxygen tank. And then, so I'm going to have 0 equals, the mass of the astronaut's 80 times, we don't know the velocity of the astronaut, plus the mass of the oxygen tank is 10 times the velocity of the oxygen tank is 2. Let's say to the right is positive, so it'd be positive 2. And so now I'm going to get 20 equals, excuse me, negative 20, duh. Negative 20 equals 80 v. And so now I can solve for the velocity, and I think you get negative 0.25 meters per second, which means 0.25 meters per second in the opposite direction. So I'm not sure who asked. Karen, are you okay with that one? Was it Karen asked?
Yeah, that makes sense.
Okay, all right. Any other questions? Okay, so then the last one we're going to do is number 3. We have this tennis player and they're returning this serve straight back. So in this one, we only have the mass of the ball. We don't have the mass of anything else. So we can't really do conservation of momentum, but we can still do impulse equals change of momentum. And this chart actually helps you with that as well. So I actually think this one's a little bit easier. So this blue is going to represent the ball, and I'm just making it 1 unit tall. And I'm saying to the left is negative. So this 30 meters per second to the left. So notice I have it as 3 units to the left. Afterwards, it's going to move, it's moving at 25 meters per second to the right, let's say. And so I have it 2.5 units wide. And so this kind of helps me visualize the impulse equals change of momentum. Be careful because it's not like you'd go 3 minus 2.5, you get 0.5. That's not true because one's going to be negative. Let's say the first one is negative. The last one's going to be positive. So it's going to be VF minus a negative VI. So you have to be careful about that one. All right, so what I'd like you to do for number 3 is set up the equation for impulse equals change of momentum and calculate the force because they give you the time. Okay, so let me stop sharing, open up the breakout rooms. This will be the last one we do. Should be in room, breakout room 8, Alyssa.
Oops, sorry.
Okay, so again, I was kind of hoping we could share our answer. Can you unmute yourself? So what'd you get for the magnitude of the force when you calculated it?
22 newtons.
22
22 less.
Good. So 22 newtons is kind of what I heard. 22 newtons. Everybody good with 22 newtons? Yay? Yeah. Okay. Any questions? Anybody need to see it? Okay. All right. So then let me talk about then what I'd like you to do then for homework. I would like you to finish those last 3 problems. Please, kind of collaborate on it. Maybe start your own Zoom session. Oops, I need to share my desktop. Duh. Sorry about that. So I'd like you to kind of finish those last 3 problems, maybe do another Zoom session with your partners and do the last 3, kind of collaborate on those. I would also like you to get started on worksheet 3. And I just want you to do it by hand so that when we whiteboard it, it'll be a little bit faster. So that worksheet's right here. If you click on this link and download, worksheet 3 is very similar to worksheet 2. Oops, right here it is. So worksheet 3. I'm not too concerned about these the conservation momentum diagrams. Like I said, if students usually find these pretty easy, but if you're like, I'm not getting this stuff, then yeah, I would suggest doing these diagrams that could help you a little bit visualize the equation. I do want you to say what kind of event it was, though. I think that's kind of important. The other thing that I would like you to do is this attendance quiz here. So let me click on this so I can give you the code. The attendance quiz is just over the kind of stuff we just did today. So it should be pretty easy. It's only, I think there's 5 questions on it. So the code, these are all lowercase letters or numbers. E is an elephant, P, 5, Z as in zebra, 5, 6, Q, Z as in zebra, D as in dog. E, P, 5, Z, 5, 6, Q, Z, D. Okay, any questions? All right, tomorrow, actually I need to get a picture before you guys leave. Tomorrow though, around 7:15, I'm attending like it's held by the College Board there and giving me more information about the test. The truth is, I could have been sharing a whole bunch of information, but myself, I feel a little overwhelmed with all the AP information, and I didn't want to overwhelm you. I know you're like, hey, you already overwhelmed me with all the all the emails. I try to condense them into like just a couple emails. So I'll give you a little bit more information, hopefully on Wednesday. That's our next Zoom meeting. Let me get a real quick snapshot. I did like the pet one last time. That was pretty awesome. Although Carter, I don't know. I mean, was that like a pet deer and then you ate it or something, or maybe? Okay. Let me get a picture. Oh, do we have another picture? Oh, yeah, we got a stuffed animal. So if you want to get something, I didn't have any cool ideas this time, but if you want to get something. All right, so let me go ahead and oh, we got a hat there. Nice. All right, let me get a picture. Count of 3. 1, 2, 3. Nice. All right. Thank you very much for attending, and I will see you on Wednesday. All right. Bye.
Bye.
Bye.